Welcome everyone. Today we're going to be talking about resonance and initial conditions. And these are two things that I raised in the previous video, and I just wanted to talk about them briefly to give you a basic understanding. I'm sure you've heard of them before, so I don't want to talk too long about it. And then after we do that, we're going to just do an example to sort of give us a holistic view of a problem that we might get for a single degree of freedom mass spring system. So starting off with resonance, we derived this equation over here, or I more or less stated it, but we derived this component, which was the root of the characteristic equation, which is the square root of k on m. And I stated that this was omega n. This is often denoted omega n, and the n is important. The n just denotes that this is the natural frequency of the system, and this is also known as the resonance frequency. So natural frequency and resonance frequency, they're interchangeable. So we want to know what is our natural frequency, and you can see that we can't really vary our natural frequency after the design stage. So for example, this K denotes our stiffness in a system and the M denotes our mass in a system. So once we've designed and made something, it has a stiffness that's set. It has a mass that's set. A great example is an airplane, or any object really, but an airplane. You know, once we've made the airplane, it has some stiffness K, which is got to do with the materials we use and the elasticity of, say, aluminium, which airplanes are predominantly made of. And it's also got some mass. And these two numbers, they're not very easy to vary once a system has been designed and produced. So this is important for us to know what the natural frequencies are. So why is a natural frequency significant? Well, the main reason that a natural frequency is significant is when a system oscillates at this frequency omega n, what happens is the amplitudes of the frequency, they can be extremely large, and this causes large vibration, which may even result in the failure of the system. So it's important for us as engineers to avoid designing a system such that its natural frequency is excited. And when I say excited, I mean that if we have a forcing frequency acting on it, then that frequency of the forcing function cannot be equal to the natural frequency, because the system has to oscillate at the frequency of a forcing function, which I described in a previous video. So what we want to do is we want to know what our natural frequencies are, and we want to avoid them. So a couple of things about natural frequencies of a system. The big one is that there's not only one often in a system. So the number of natural frequencies in a system is equal to the number of degrees of freedom in that same system. So degrees of freedom often denoted DOF. So if we have a single degree of freedom, which is just SDOF, like the spring mass system, this just has one coordinate that can describe the position of this mass. This is a single degree of freedom. So if we have a single degree of freedom system, we have one omega n, one natural frequency. If we had a system with 2 degrees of freedom, a great example would be a spring mass with two masses. So we need two different dimensions for this, say x1, and say this one here is x2. This is a 2 degree freedom system, which is often you might see MDOF, which is multi-degree of freedom system. So in this case, we have two coordinates representing two masses. So we're going to have 2 omega n's. And this goes on and on and on, so up until when we have infinite omega n's. And a system like that is a beam. A cantilevered beam is a great example of that. So theoretically, we can define on this point any slither of mass and give it a separate coordinate system. And this means that there is infinite coordinates on here. So that means we have infinite omega n's. So you can see that as our systems get more complicated, we get more and more natural frequencies. Now, the natural frequencies are predominantly most disruptive at the lower frequencies because the amplitudes are much higher, and that's often where we tend to see them. So it's just important that we know where they are and we can work around it. So basically that's natural frequencies. We want to be able to calculate them and avoid them. So you can see that from this little example here that there are many different natural frequencies, and the types of systems we have are important, and we have to consider the system's geometry and the degrees of freedom. I might just give a quick description of exactly what degrees of freedom are. So if I draw a box, and this is just going to represent a point mass. I'm going to draw in pink here. So our box can move up and down. It can move left and right, and it can move into and out of the page. Okay, so this is typically Z, Y, and X. So these are 3 translational degrees of freedom. And then we can also have, well, it can rotate this way. So the box rotates this way and that way. The box can rotate up and down. So the back can go to the front and the front can go to the back. And it can also rotate horizontally. So around this axis is Z axis. So we have 3 rotational degrees of freedom. So you'll see that a point mass can have up to 6 degrees of freedom. Now, that's why we restrict most of our problems to single degree of freedom system, because this would technically could have up to 6 natural frequencies. So I've just come down and drawn these 2 diagrams here, and I want to talk about initial conditions. So we have this diagram on the left here and this on the right, and we can see that I'm denoting that MM and KK, so these masses are both the same. The spring constants are both the same in both diagrams. The only thing different is that we have an initial displacement here for this system on the right. So this is where our initial conditions come into play. So on the left here, at time is equal to 0, the mass is on the datum point, our reference point, which is x of t. This is just equal to 0. There's no initial displacement. And I'm also going to denote the first derivative, which is the velocity of the mass at time 0 is also equal to 0. So this mass here is not moving, and it is starting from 0. On the right here, I might say that x at 0, now this is positive, is equal to, let's say, minus 0.5 meters. And all that means is that my mass is starting at 0.5 meters. And the minus is just there because we are assuming that down is positive. So it's starting up. So let's denote the velocity of this mass as also equal to 0. So this mass here is starting from rest with some initial displacement. This mass is starting from rest with 0 initial displacement. So from last lesson, when we derived the general solution to a single degree of freedom spring mass system, we had A cosine omega nt plus B sine omega nt. So these 2 systems are both single degree of freedom systems. They both have the same natural frequencies because I've said that M and K are the same. So when we look at this equation here, they must vary their constants because we can't change time's the same for both of them, and we can't change omega n because it's set. So to derive the solution for these equations, we have to consider these initial conditions. And the way we do that is we take our general solution, and we differentiate it and let these conditions come true. So say we have system 1 here, and this is system 1, and this is system 2, and we'll focus on system 1 first. We want to plug in our initial conditions into our general solution to solve for our unknown constants. So x of 0 is equal to 0, which is according to our initial conditions, which is also equal to a cosine omega n times 0 plus b sine omega n times 0. Now we can see that this is going to equal 0 inside the sine brackets, so this is 0, and we can see that the cosine here is going to equal 0 inside the brackets, which gives us 1. So this just gives us a equal to 0. All right. So we found our first constant. So now what we have to take the first derivative of a general solution. Now I'll just write out the full derivative first. How about that? Minus a. Now the derivative of a cosine is a sine, negative sine, omega n t. Now we need to bring out an omega n as well, plus b cosine omega n t, and have to bring out an omega n. So now we know that a is equal to 0, so all we need to focus on is this right hand side, and we know that let's plug in our initial condition. We know that the velocity is equal to 0, which is equal to, now I'm not going to include this component because we know a is 0, is going to be b cosine omega n times 0 times omega n, which is going to equal 1 because omega n times 0 is equal to 0. So what we get here is we get b omega n is equal to 0, which just gives us b is equal to 0. So we've found both of our constants. They both equal 0. So now what we have to do is we plug back into our general solution. So this gives us x of t is equal to 0 because b is equal to 0 and a is equal to 0. And now this might seem wrong or it might seem trivial, but let's look back to our initial conditions. We have our initial displacement is 0. So our mass has not been moved from its datum. Its velocity is 0, so it's not moving anywhere. So when we plug in any time, because we haven't moved the mass or excited the mass in any way, it's just going to be stationary, which means that our displacement at any time t is also 0, which is just stationary. So this is just an example of initial conditions. So now we're going to compare the second system to our first system, and we'll show the difference in initial conditions can make. So x of 0 is equal to minus 0.5, which is equal to a cosine omega n times 0 plus b sine omega n times 0. Now, same as before, this goes to 0 and this goes to 1. So this gives us A is equal to, okay, so we've got our first constant. So now we want to find out what the B constant is, and we're going to use this initial condition for velocity. So because looking over this side, we know that when we plug in x's times 0, we know that this sine term is going to go away. So I'll just plug it into here, into this cosine term. So the x dot of 0 is equal to 0, which is equal to b times cosine omega n times 0 omega n, which is going to be equal to 1, which gives us the same result as before. B omega n is equal to 0, which gives us B is equal to 0. Okay, so now we just write our final equation for the second system. So we know that we just plug everything back into our general solution. So x of t is equal to minus 0.5 times cosine omega n t. And now I defined this in meters before, so always include the units in meters. And this is our solution to the system. So I hope this shows the differences our initial conditions can make. We've got the same mass in both systems, the same spring constant. The only difference is we have moved system 2 with an initial displacement, and look at the difference. We have harmonic motion for system 2. It's moving up and down as time goes on. And on the left-hand side, we have 0. There's no motion there. So it's very important that we consider our initial conditions as they make a massive difference to our final answer. Okay guys, thanks a lot for watching. I'm not going to get to the example in this video because we've run a little over time. But next video, I'm going to do a couple of examples to make up for it. And yeah, I hope this really helped. Please like and subscribe if you did find this helpful, and I'll see you in the next video.